All right, welcome to another exciting presentation of Mr. Szymanski isn't here, but I still need to learn stuff. Today's exciting lecture will be on dun, 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 Newton's third law. And to help us today, we'll be using our butterfly. There was such raving reviews over the duck, I decided to pick another ridiculously cute animal. So it's a butterfly, and if you don't believe it's cute, come on, look at that face. It's cute. Okay. So, whoops, uh-oh. All right, so here we go. Newton's third law. Now, you've probably heard this in your grade school, elementary, I don't know when. It was probably once described to you as this. For every action, there's an equal and opposite reaction. That's what it says in textbooks. That's what you might hear other people say. That's what you've been told. That is a giant atrocity to what Newton's third law actually means. Okay, because that often puts bad connotations in your head. This often makes people think of, wow, if I make the butterfly move, it'll make me move or something like that. Like I punch you, you get to punch me back. No, that's not the way it works. So what we're going to use for our understanding of Newton's third law is we're going to go back to our definition of forces. I lost the bug again, dang it. So we're going to say this. Okay? Force, we remind ourselves, the definition of force was a single interaction between two objects that results in a push or pull. Okay, if we look at this right here in our definition, it says that we have a single interaction between two different objects, aka two objects touching one force. All right, so to help explain this, we have a demo. All right, oh, that's what I wrote there. So this means if two objects come in contact with each other, they will instantly apply the exact same force. Butterfly. Oh, you have a bug down here. Cool. You have a multiple bug system. So here we have a truck, okay, big truck, okay. Truck comes along, sees the bugs, okay. When the truck comes along, I'll leave the butterfly out of this, okay. Here's the bug. All right, truck comes along, smack. All right. What type of force do they experience when the bug goes smack onto there? Well, let's see. Two objects, one interaction. If we're going to write this in physics terms, it would look like this. All right? We have the force on the bug by the semi. Well, we also would say, well, I'm sorry, Mr. Semi, what happened to you? Well, I had a force act on me, the semi, by a bug. All right? So pretty much, we've got these two things. Mr. Butterfly says, let's check it out. We got a bug here and a bug here. That's one object. We've got a semi over here and a semi over here. That's two objects. 1 plus 1 is 2. Good job, Mr. Butterfly. So we have exactly two objects equal how many forces, Mr. Butterfly? 1. Good job, Mr. Butterfly. Two objects only equal 1 force. All right? So you get two objects, 1 force. So the question is, well, which hit each other harder? Well, they hit each other with the exact same amount of force. The only difference is the semi is freaking huge. So when it hits that bug, the bug will obviously go, you know, let's just say splat. Okay? So the result of this force might be something different. Okay, we have a dead bug. Dead bug. Checking out the autopsy photos, it's dead. Okay, semi looks fine. Okay, semi seems to be fine. All right, so you've got a dead bug and a fine semi because the results of that force could be totally different. All right, picture Mr. Szymanski hitting a freshman in the hallway, unintentionally, of course. I'm not going anywhere, the freshman's going flying. Okay, now we could also say, well, let's, you know, oh, look, the bug's back alive. We could have two bugs, and they're going to sumo wrestle each other for it. Let's flip, left, right. Okay, challenging. Okay, they could challenge each other. Now they hit each other. Okay, how do their forces compare? It's the same. They both have the exact same force applied to each other. But two bugs slamming into each other might look a bit different than a bug slamming into a semi because they're obviously different objects, different masses, different sizes, all sorts of different variables at play. So the key thing you need to walk away with is this fact right here. Two objects result in one force. That's really Newton's third law. Okay? So let's just check this out with some finer understanding here. All right, so here we've got a little tug of war here. All right, we got tug of war. And we've got, let's see, we've got Walter versus Smith. What can I say? I just bought furniture, okay? So we've got Walter, we've got versus Smith. They're in a tug of war contest. So let's see. Let's just think about this. Walter's pulling on Smith. We only have two objects. Oh no, I lost my bug. I just realized I lost my bug. I have to save him. Where is he? Copy. I need to right click on something. Come on. Lock. Yeah, unlock. All right. Right click. Paste. Paste. Where's paste? I have lost the bug. Paste. Where the heck? Oh, found him. Okay, the bug is back. Okay, for a minute I was really worried the bug is back. Okay, so bug is being official here. So normally, Walter tugging on Smith here. We have one rope, okay? There's only one rope. What are you doing? No. All right, we only have one rope, a single rope, so it can only hold one force. So if it can only hold one force, then they must be pulling on each other equally. But then how can I make strange things like this happening, where they're pulling on each other? It's going back and forth, okay? Smith just yanks, all right? Walter just fights back, all right? They're going back and forth. They're tugging, they're tugging, they're tugging. Well, who's pulling on each other harder? The correct answer is each applies the same force to the other. It's like a trick question, okay? But then your brain's probably thinking, Mr. Szymanski, if they're both pulling on each other evenly, how can Smith win? How can Walter win? Heck, how can they move? Okay, how can you have like one just go yank and yank, okay? How can that even happen? Well, you draw a force diagram on them. So let's see if I can use a little better position here. So if you draw a force diagram on them, then you've got, well, acting on Walter, we've got force of gravity, force normal. He's pulling on the ground, okay, so we've got a force of friction. And then we have, obviously, the force of tension. Well, acting on our friend Smith here, we have force of tension, happens to be the same one as before. Force normal, pushing him up. Force of gravity is pulling him down. And then he's working back with the force of friction. Now, again, you have to like, Mr. Szymanski, all these forces seem the same. Well, that's where the on-by notation is so crucial. This is force of tension on Walter by Smith. All right. This over here is the force of tension on Smith by Walter. Again, same two objects, therefore there can only be one force interaction. Okay? But, and a force of gravity on Earth, but we really don't care about the up and down stuff. If you look at the force of frictions, though, this is the force of friction on Walter by, we'll call it the ground. It says ground. Trust me on that. It says ground. Whereas this one over here is the force of friction on Smith by ground. Well, looky here. We've got Walter, ground, ground, and Smith. That's more than two objects, folks. 1, 2, 3. That's 3 objects. Okay? So we've got 3 objects, so we can have more than one force. So this is why in a tug of war, it's not you pulling on the other guy more because these are the same. Okay? 2 objects, 1 force, 2 objects, 1 force. It's just seen from a different point of view. You know, I hit you, you hit me, whatever. But with the other one, we have 3 objects involved, so we have multiple forces. So this is why when you do a tug of war, you want like the big fat guy, like Mr. Szymanski, pulling because he can apply a greater force of friction on the ground than, say, the small little dude or butterfly. Look, he's Captain Butterfly now. Okay. So that's the big thing, okay? On-by notation is so crucial. If you ever do on-by notation and you only have 2 objects involved, that's going to be the exact same force. It doesn't matter if it's moving with constant velocity or accelerating, okay, or speeding up or slowing down or just standing still, okay? No matter what, same force, same force. Because no matter how I draw it, those 2 forces between the rope will be identical. What makes them move are the other forces in the plane, like friction. Okay? So that's pretty much the big thing with Newton's third law. You just got to kind of say, hey, how many objects are involved? How many forces that result in? Done and done. So I think that's about it. That's all I got. Bye-bye. I'll see you guys later. Done.